All right, we're on? But yeah. All right, so thanks to the survivors for staying through, yes. So today I'd like to do two things. Well, the title you can see is the curved Cartan complex. Just to remind a little bit in terms of style what happened, I gave, I think, probably 2 lectures which contained a lot of definitions, maybe too many of them, and then the last lecture was sort of pictures, and even though things could be made precise, it seemed to turn a bit wishy-washy, flippy-floppy, the kind of thing Sarah Palin wouldn't stand for. So I thought in this lecture I'd have to, part of what I want to do is come back to something very solid, very precise, the thing that allows you to calculate things in this world of group actions on categories and be dead sure that you get the right answer or get the wrong answer, but you get an answer. So there's no guessing involved. And then I will relate that back to the picture of Lagrangians in that BFM space and to the Kapustin-Rozansky theory, and we'll review that a little bit in conclusion, review the story of two-dimensional gauge theories. Finally, I'll give a lower decategorified one-dimensional picture. Once you understand a two-dimensional picture, it turns out there was a one-dimensional picture completely analogous to it, but I would have been crazy to talk about it, I think, in that setting. There's a reason why it's somehow not interesting. Again, it's a mod 2 reason somehow. But first, I'd like to introduce the curved Cartan complex. So we're starting with a compact Lie group G and an infinitesimally trivialized G action on a category C. I'm going to apply to locally trivial action, which is a stronger condition, but all you need to run the construction is the infinitesimally trivialized condition. So the C cube, the curved Cartan complex, is a specific model, Kojoule dual, the standard model, a specific model for a derived quotient category. C, the co-invariance under the Durham group stack of G inside C. So co-invariance under G in the world of locally trivialized, infinitesimally trivialized actions. There's an obvious model, the homotopy theory tells you to use, which is essentially a cross product of the group with the category. We've described that for a discrete group here, described it explicitly, and now we know how to convert that to anything. I mean, you just go to the Grothendieck site of analytic spaces or smooth manifolds or whatever, and you can form this cross-product construction from a sheaf of categories and the sheaf associated Durham stack of the group. So if you want a concrete model, which is much more useful for computing, you can do that. The group algebra of this Durham group stack, G mod its formal group, that's what you need to form the cross product. The group algebra is a chain complex, the complex of chains on G with a convolution product. And this has to be added to the home spaces in the category. That's how you define the cross product category. You keep the object but add morphisms coming from linear combination of group elements. They become chains on the group. So that I'm saying is a Kojoule dual model. If you want to push this abstract point of view, you can find an interpretation, a reinterpretation of this obvious model as a homology of the classifying space BG with coefficients in the sheaf C of categories with connection. The locally trivial, infinitesimally trivial action of G on C gives a sheaf of categories over BG, but with a flat connection.
Sorry.
Yes?
Is this obvious model obvious? I mean, to give it infinitesimally
yes. The obvious model is obvious in the sense that that's how you form the quotient. Well, it's obvious from the definition of the quotient category, but there may be other points of view in which another model is more obvious.
But I mean, an infinitesimally trivialized action is not just an action of this chain complex, right?
It's an action of this group, the Durham group of G.
Right.
That's correct.
Not just an action of its group algebra.
Not sure I understand. If you have an action of a group on the category, that's how you form the quotient category. That's why I would form the quotient category. But this means, I mean, well, what would mean strictly speaking, compactly supported functions on the group with values in the category, and then, well, in the algebra, if it was an algebra, it's easier to say, and then you multiply them in an obvious way. So compactly supported functions on G, I'm identifying with chains with convolution. I think what you're sensing, what you're spotting is, of course, the danger, the dangerous path it leads to if you start replacing this with various chain equivalent models. That's completely correct. That's why we're not using this, we're using that. But this is what, I mean, from first definition, this is what somebody would be writing down. So what I would be writing down. You can interpret it in something more, in a more sophisticated way as chains actually seen on BG with coefficients in C. This is slightly wrong. You have to interpret BG in a stacky way. If G is not connected, then you do want the group to show up as a fundamental group of BG. So if G is not connected, chains on BG does not remember the group very well. So this is this might be a tempting thing to write, but to get back to this, you would have to actually work. This is the standard. I maintain this is the standard thing to write for the quotient algebra. If you want a precise model for this, you can take essentially you can take the RAM forms with convolution on the compact group, taking advantage of the fact the group is compact. All right. So the Koszul dual in the curved Cartan complex, you place chains on the group. That's the thing that David was probably worried about. Chains in the group, the homology of the group by the cohomology of BG. That's what Koszul duality actually does. This guy is actually always an exterior algebra, free exterior algebra, and this guy is always, let G be connected, this guy is always a polynomial algebra in generators that are matching the generator, the homology of G. So for a generator, an odd generator here of degree K, what you do in Koszul duality is homological degree K, you flip, so you get cohomological degree K and add 1. That's what you would do in Koszul duality. So maybe I should, is everybody familiar with Koszul duality? No. Let me just say the words, otherwise it makes no sense. So example, it's only one example we need to know of Koszul duality. It provides an equivalence of DG categories. You have to start being careful how to saying that, between sim V modules and lambda V, maybe we'll write it this way, sim V star and lambda V modules. And this is the category localized at 0. So you could say there are several versions you can say now, depending on which finiteness condition you choose. For example, finite dimensional on this side corresponds to perfect on the other side, as an example. And the equivalence is, can I do the equivalence? Well, let's go this way. Module M goes to X over lambda V of K into M. And this is a module over, I should write R hom. I'm sweeping over a difference between derived and its homology. It's a module over X over K over lambda V of K with K, and that is of course sim of V star. That's the equivalence. So that's how it goes. So to interpret this correctly, if these have even degrees, so if generators here have degree 2k, you understand that generators here have degree, well, minus 2k plus 1. Cohomological. Dualizing on the flip side of a degree, and the symmetric to exterior is a degree shift. And in fact,
I've seen before, but it still looks this way. Because the left are basically polynomials, right? Everything is
modules over polynomials, yes.
so like you take some variety.
Right, so it's the category has to be localized at 0 in V. What you're going to see here is only the germ of anything you have at 0. You're going to see that on the other side, but you're not going to see anything far away. And it's perhaps slightly better if you remember these are graded in this sort of a C-star scaling action. So you ask that this should be homogeneous and they should be cones.
Oh,
and in that case, obviously all the information is at the origin, and then you're good. That's much easier. But you don't have to ask for that, for homogeneity. But then, of course, from this side, the left side has a lot more information than the right side for obvious reasons. This only, because you're seeing basically, here you're seeing the only homes from K, the augmentation ideal, the augmentation ideal, well, the other direction. You can do it with an X or a Tor, and I don't know which one I want now. But anyway, you're also going to use tensoring over sim V star over K, or I forgot which way you have to do it to get it to work nicely. X over sim V star from K into dot. One of these functors. So you can only remember what is seen by tensoring with the skyscraper at 0, or homing from the skyscraper at 0 on the other side. So there's lots of information from left to right. Okay.
Even though both sides are equivalent.
They're equivalent. The category localized at 0. Sim C modules, that's part of the statement. Localized at 0. Localization at 0 essentially loses all the information we're talking about, information away from 0. You declare two things. You declare a map between two modules to be an isomorphism if it's an isomorphism on the fibers at 0. And after, that's right, exactly. After you do that, then this category becomes equivalent to that. Exactly, that's right. So there are some situations where it's fine. I mean, if you only care about information at 0, in the graded case, that's good. But that's exactly going to be the point of, instead of using this, what I call the obvious model, of using the Cartan model. Because this guy is, the symmetric algebra is much bigger than the exterior algebra in terms of its modular category. And the virtue of this will recover the correct gauge theory of a point or vector space, the only ones I can honestly compute, also known as the A model with topological twist. And I'll discuss the Casimir twist in particular. But if you're going to use the obvious model suggested by homology theory, you get the wrong answer, and if you're going to use a curved Cartan complex, you get the right answer. That's sort of the point. Okay. You're not happy about something?
Yeah, I'm not sure. I still don't understand why the obvious model is the right one.
Well, it's obviously not. I mean, that's the last sentence says not if you want to do gauge theory, but it's the right one in the sense that if you want to derive in that category, I mean, that's, how else would you do it? I mean,
tensor product. You can see tensor of a trivial category as modules over D modules on G.
But we're not acting with D modules on G. We're acting with G.
Infinitesimal trivial actions.
No, I'm not taking. If you call limit complete, if you're doing lots of things, but you're right. You should call limit complete this.
Yeah.
That's correct. I agree. If you call limit complete this, probably you get the same thing. Yeah, if you call limit complete, I think then I don't think we disagree. You still have the same problem, whether it's D modules or G or anything else, by the way. All right, so let's write a definition. So, what was the point of a cross-product algebra? Was that G cross A modules was G invariant in the category of A modules. That's a point of a cross-product construction. And for simplicity, I'm going to fix that situation. So I'm going to assume that my category had a single object with an endomorphism ring, which is a DG algebra, just to make life easy. So that corresponds to the case where you want to compute the fixed point category inside A modules. And you do so by writing modules over the cross product. So I'm going to replace this. The point is to replace that with a curved Cartan complex, and then the fixed point category of G mod G hat acting on A modules would be defined as a modulus over the curved Cartan complex, over the replacement of this, big replacement of this. So the setup is that G acts differentiably oops, G acts differentiably on the DG algebra. So the infinitesimal action is given by Hochschild 1 co-cycles, so a Lie algebra map from G to the Hochschild 1 co-cycles with the Gersten-Haber bracket. That's intrinsically defined in Hochschild cohomology. So that's a differentiated action. And this differentiated action is assumed to be trivialized by a map iota from the Lie algebra to Hochschild 0 cochains, such that the pair iota L from the equivalent to 0 DGLA involving two copies of G, so this one is in degree -1 or homological degree 1, this one is in degree 0. So it's a model for the 0 Lie algebra. This defines a Lie algebra map, DG Lie algebra map to the Hochschild cochains, which is the equivariant for the action of G. Okay. So in other words, the action of G via L, which was a map to HZ1, has been factored through 0. That's what trivialization means. And from this, we can form the following curve DGA. I'm writing a simple example. I'll tell you about the quotient later. So the DGA is the cross product of G with, I wrote A tensor polynomials on G, but here you can and will have to be more generous and say allow holomorphic functions on G with values in A, cross product with G. The differential is going to look like a Cartan differential. So it has this internal differential of A. And now I'm writing a Cartan style term, which combines the linear generators. I didn't write. Psi A is a basis of. Did I write it anywhere? I did. Right here. Choose a basic psi A of G and the dual basic psi upper A of G star. And then you can couple the iota action to the linear generators in sim G star and add that as a term the differential. And if you remember formulas from equivariant topology, d squared does not square to 0. Instead, d squared squares to a commutator with an element that you can write down, w, and that is the sum of the linear generators in G star with, well, essentially with this L, guys. But what these L's are, there are derivatives of the delta function on G in here. So they're in this big cross product algebra. So the commutation of this guy with A will be the action L of psi A. And they satisfy the curve DGA relations that d squared is commutated with W. So it's not a DGA, it's a curved DGA right from the start, right off the bat. And I've cheated in one place. I wrote what you would write in the simplest example or most standard example. But the reason this iota term appears in the differential comes, well, it will only show up in the degree 1 the differential if as a Hochschild cochain, it has Hochschild degree plus 1. In other words, if it's a derivation, honestly. That's why it can be part of a differential. And the next example, the standard example, will see that. In the standard Cartan example. But in general, you see the 0 here combines the Hochschild degree with the internal degree of A. So in fact, iota could be all over the place in terms of Hochschild degree. And if it is all over the place, you have to distribute it, break it up in Hochschild degrees, and the various parts define various bits of an A infinity algebra structure on this. So this in general will be a curved A infinity algebra. I don't know natural examples where it shows up in places other than 0 or 1, but we'll see an example where iota actually shows up as a curvature. Okay, any questions about the formula because it's going away? So if you know the Cartan model of equivariant cohomology, what you would be doing here, instead of doing this, you would write this, take invariance, and then this squared would be 0. And that'd be a complex and you'd be happy. And that's not what we're doing. We're making it to a curved algebra. It's not clear why, maybe. Why is because if you try the other thing, you'll get the wrong answer, but you have to try it and calculate it to see that. Alright, so first example is a Cartan example. So G acts on a smooth manifold X. Take the algebra of the RAM forms on X. Then L psi is of course a Lie derivative by the vector fields defining the action. Iota of psi is a contraction of the same vector fields. Notice that as far as the algebra goes, it's a derivation. It has Hochschild degree 1, but it has degree -1 because it's odd. It reduces the form degree by 1. So derivation of degree -1. So it has total degree 0, but Hochschild degree +1. And d Cartan is given exactly by the formula I wrote, and squares to psi a times L the Lie action of psi a. That's whose formula is that? It's going to be d bracket contraction is Lie derivative. Lie's formula, Cartan formula.
So what's Hochschild mean here?
Hochschild degree means it's going to be a map from A to A. So that's as a Hochschild cochain, the degree is 1. It's a derivation. But the derivation of degree -1, the total degree is 0. It's where it's supposed to be. But it goes in degree 1, the differential, because that's the kind of thing it is. And d Cartan squared is commutator with this combination, the curvature, so the linear generators in G star, times the derivative of the delta function, which really means the Lie algebra elements inside the distributions on G. If you wanted to compute equivariant cohomology, as I said, instead of doing this, you would be taking G invariance in this times in G star, and just then d squared is 0, and just compute cohomology. But that would be the vector space story instead of the algebra story. Okay, let's do a trivial example where A is the algebra C. The algebra you get is a cross product of G acting on the function on its Lie algebra by the adjoint action. It has a curvature, this quadratic term, bilinear actually, one direction on the Lie algebra, the other direction in sort of inside the, if you like, the universal enveloping algebra on the group. So one factor from here, one from there. And it turns out, not completely obvious, that modules of it are equivalent to modules over the invariant part. It's a curvature which does that magic. It'll be obvious for a torus in a second. So let's look at the torus. In that case, we can write the cross product algebra very easily, okay? Because the action is trivial. So in fact, we get the group algebra of T tensor with functions on the Lie algebra, and the group algebra of T is just the sum of copies of C indexed by the characters. So its spec is just this joint union of copies of the Lie algebra labeled by the characters of T, and the curvature on each sheet restricts to the corresponding linear function. So psi goes to lambda of psi. And linear functions have no critical point unless they're 0. So all the sheets except the 0 sheet disappear. And the 0 sheet just gives you the modules over sim T star, which is the cohomology of BT. Right. So if you generate from here a two-dimensional field theory, that arises by gauging a point, basically. If you ask what two-dimensional topological field theory you're generating from this, it's not quite a topological field theory, it's not quite finite enough. Just short of that is the string topology of BG, of the classifying space. It's meaningful, it's a little bit infinite, which you could kind of suspect because you see this big algebras appearing. Okay, let's do a non-commutative example where the iota contributes to the curvature instead of a differential. So I'll take the algebra to be the universal enveloping algebra and G to act by conjugation on it. So the Lie action of G, the infinitesimal action, is just the commutator bracket from U to U with some element psi. And it's trivialized by the map iota of psi is psi in U. A Hochschild 0 cochain, an element of the algebra this time. But it has Hochschild degree 0, so what it does, it doesn't contribute to any differential. There's no differential, there's no grading anyway. Well, actually there is here, but it's even, so there's still no differential. These guys have degree 2. I should have said that. There's no differential, but there is a curvature, and it's the original term, the original curvature term you had, the distribution on G times the linear generator, minus it's going to be iota times psi A. To spend a bit of time on the sign, but I think there is a convention clash. In curved algebra, you write d squared is commutated with w. In infinity algebras, you write d squared plus commutated with w is 0. So there really is a sign issue, I think, in the conventions. Now it turns out the modules over this are equivalent to G representation. So the category of modules over this complicated curved algebra gives you just the category of G representation, and the curvature is going to force a cancellation between U of G and sim G star. People who know about Knoeller periodicity, coming up in a second, could at least guess that. It's a non-obedient version of that, so it's not a bit less obvious. But if you want to compute it, you compute the Koszul dual model, and the Koszul dual model, this guy becomes actually a differential, which cancels U of G and the exterior algebra. Okay. Now let's get back to examples we're interested in, which have to do with, say, mirror symmetry and torus action on manifolds. And let's talk about the torus. So the first example I'd like to go over, but maybe before that, any question about what's happened so far? Other than where it is going. It's connecting back with the story in about one page. But I wanted a precise definition, so it's not just this is sort of like a Lagrange and some cloudy lift of it intersecting something else in a space we can't see. So it has to be something a bit precise here. Okay, so let's talk about the regular representation of T locally trivialized, of T loc. I should make it precise. Of T loc. T mod T loc, that's how we're writing it, although. So we said that the representations of these are module categories over the tensor category of coherent sheaves on T check on the dual torus. So from that perspective, the regular representation should be the category of coherent sheaves as a module over itself. So let's spell out the action of the group so we can actually compute something. It's enough to spell the action on the Lie algebra, then you get it on the category of modules. And that's hiding inside the Poincaré bundle over T cross the dual torus. And you have to make this Poincaré bundle flat and multiplicative along T. You have to give it a flat connection along T and make it multiplicative, meaning define a family of coherent isomorphisms, P sub T, which means P restricted to T cross T check. P sub T tensor P sub S should be made isomorphic to PTS, and they should be coherent as far as you can write. And if you have that, then the action of a group element on the algebra of functions on T is tensoring with this line bundle. It's a bimodule. It's not by a map, it's by a bimodule. So it does nothing to the algebra, moves nothing. Like one of these magic tricks. I mean, you see the magician doing something, it seems to do nothing there, and suddenly the coin is behind your ear. So nothing moves if you look at what the group element does, but at the end things are twisted. So for each group element of T, I'm giving you a bimodule for this algebra, and that's namely the line bundle PT, the fiber of Poincaré over T cross T check. And you have to trivialize it on the Lie algebra, and that you do by choosing a path between 1 and T and following the connection to create an isomorphism between the line bundle P sub T and the trivial line bundle. And then you have to do a little calculation. You have to find the cross product algebra, and that turns out you might have thought because there's no movement, they just get the group ring of T times functions on T check, but there is a twisting in this action. What you get is you unravel the functions on the dual torus to functions on this Lie algebra. That's what happens. And the curved Cartan complex of this is now going to be the functions on t check cross the other copy of t, that's a sim t star, and the potential becomes psi a, so the generator, linear generator on this factor, times psi lower a, that will come from the flat connection compared to the group action on the Poincare. And there's so it's this non-degenerate perfect quadratic pairing on the space times its dual. And the theorem that Orlov calls Knoerer periodicity, from the world of matrix factorization, identifies the curved module category with just the category of vector spaces. So we've just shown that the fixed point category inside the regular representation is a trivial representation, which with multiplicity 1. So that had better be true, right? It's a kind of statement we like about groups. But now you can generalize it to Landau-Ginzburg models. If the action of T comes given as a holomorphic map from the mirror to the dual torus, and you have, say, a potential on the mirror, then when you form the cross product in the same way of T, the action of T with Y, you get the covering space of Y pulled back from the universal cover of the dual torus. So you have a map here, you pull back, you get a Y tilde. And the curved Cartan complex is again, it's going to be nice and easy, no differentials. It's going to be just this space, this cover Y tilde, crossed with a copy of the Lie algebra with potential, whatever it was before, plus the non-degenerate quadratic term. And another little theorem, which is maybe a cousin of Knoerer periodicity, tells you that this is the equivalent to the Landau-Ginzburg model on the scheme theoretic fiber of the map from Y to T check, or from Y tilde to the Lie algebra, if you prefer. Actually, it's probably equivalent to an X if you do it right, whereas the quotient would be a Tor, but I don't want to confuse myself. So this Cartan computation, if you unravel it, has the virtue of doing what we always knew in mirror symmetry, and to get the quotient, to take the fiber over 1. Just get to it in a very roundabout way. But it's a sanity check. You better recover the known example. All right, questions here? Still no questions. All right. What am I doing? I'm going to borrow a line from Ed Witten in his talk and say that if there are no questions, I'm going to assume that everything is crystal clear. So now I'm going to finally introduce something a little bit more interesting, because without that we cannot gauge a point. Not really. And that will be the key to understanding that global space, that blown up cotangent bundle of conjugacy classes that I talked about last time. I'm going to give meaning to why points in that space say something about quotient categories and gauge theory.
Sorry, which space?
The BFM space last time, cotangent bundle of G check mod G check. Or cotangent bundle of a dual torus if you prefer. Okay, so let's start by recalling a basic fact, namely Gromov-Witten theory of a variety X, let's say compact, has a natural family of deformations, which I'm going to call topological twists. I'm sure it clashes with a million other topological twists, but for today let's call them that. And the deformations are parametrized by the cohomology of X, or by a part of it. That's going to be the Frobenius manifold, of course, of the theory. And geometrically you define them as follows. Okay? So let's recall that to construct Gromov-Witten theory, for every fixed genus and every n number of points, you're going to form the space of stable maps, or stable curves, I should have said, because we let the curve vary as well. Stable curves in X of genus G with n marked points. Now assume you have chosen n plus 1 marked points, and you map this to X by evaluating a curve at the last marked point, seeing what the last marked point was. And let's choose also a class in the cohomology of X. And now you define the twisted Gromov-Witten invariant by using this thing, where in Gromov-Witten theory you are using the virtual fundamental class of this space of maps to integrate and produce a numerical invariant, which then gets packaged into some generating function, blah, blah, blah. Instead of using the virtual fundamental class of this space to integrate, you're going to cap it with the exponential of the push down of f star alpha along the forgetful map. So xgn plus 1 bar, the forgetful map has one-dimensional fibers, has a curve in the fiber almost, and we're pulling back a class to the total space, and we're integrating it along the curve over xgn bar, but you have to say it in this complicated way because the curve also moves, right? Of course, if you fix the point xgn bar, you fix the curve, and you're integrating along it. So why would something like this be even considered? Well, this integral, of course, is additive in the piece of curve. That's how we integrate. So when you exponentiate, it becomes multiplicative, and when it's multiplicative, it has a chance of being a topological quantum field theory. In this case, it is. So in the gauge theory of a point, doing these operations, starting with cohomology class in BG, so X will be BG in that sense, point mod G. Doing these operations will lead to Witten's integrals on the moduli of G bundles, coming from class in BG. In fact, if you don't do this and you try to literally take the Gromov-Witten definition and integrate, you'll find that you get 0 all the time. You have nothing to integrate somehow. And it's only after you introduce these twists that you begin to get differential cohomology classes which have a volume form, have a top form that could give you a non-zero integral. So for example, if you start with a quadratic Casimir in H class in H4 of BG, coming from a trace form, what you get on the moduli of bundles is the symplectic form, the Chern class of the theta-aligned bundle, exactly by this construction. Okay, so this exists. Given the variety X, you have this whole family of topological twists. So in particular, for point mod G, you'll have these topologically twisted A models. And they all must come from, we believe, from a category of boundary states. So the question becomes, what are these twistings on the category of boundary states? Okay, now here's another question. The curved Cartan complex of anything allows to add additional curvatures. I mean, now once you have a curvature, you can ask what happens with other curvatures. Namely, the invariant functions in the Lie algebra live in the center of the algebra I wrote, so you can always add those to the curvature. They're all central elements. So the question is, what effect do these have on the fixed point category computation?
So just to get granted, what would have been the answer to the first question if X was just an actual variety?
This you would be moving inside the Frobenius manifold of quantum cohomology. That's all. So it's a big quantum cohomology. If you start with small quantum cohomology and this was not a degree 2 class, you'd be getting the big quantum cohomology. Oh, the first question, sorry. The Fukaya category also, right. Okay, the abstract nonsense answer is that it is believed, widely believed, in some cases proved, that the cohomology of X is the Hochschild cohomology of the Fukaya category of X. Therefore, it parameterizes deformations almost by the infinitesimal deformations. It is also believed that deformations are unobstructed. Therefore, there is a moduli space, which is a germ of H star of X. But to answer more precisely, you can go down to Earth, and pretty much what you are doing here, you can do in the Fukaya category. Meaning, instead of just counting holomorphic disks when writing the Floer complex, you're going to take the moduli space of holomorphic disks and integrate classes over them. So higher dimensional moduli space of disks begin to contribute the Floer differential. I don't know much about the status of for what case this is proved. I would suspect the Toric-Fano case is close to being under control, but there's probably 1,000 pages of Fukaya auto. I shouldn't have started now. Otsugu? No. Otto. Okay, thank you. All right. FL cubed, as people like to say. And now I know why. All right, sorry. Very bad. Alright, so question 2 is what effect do these curvings in the Cartan complex have on the fixed point category? And by now we've already noticed that the origin of both questions in the case of gauge theory is homology of BG. So the two questions, of course, answer each other, or else they would not be on the same page. In other words, adding these functions as additional curvings, the Cartan complex implements the deformation, this topological twist in the gauge theory. And that's actually a precise, absolutely precise, crystal clear theorem, at least with some qualifications. Let me just talk a bit about the quadratic Casimir, because that's a very good illustration, and somehow it's the most important twist, and everything is sort of perturbed from that. So in this A-model gauge theory, if at least if the action isn't free, so if you have a positive dimensional stabilizer group, you render a theorem meaningful by the quadratic Casimir twist, and then you can study perturbations away from that. And it has a dramatic effect on the quotient category vect on G, namely it makes it semi-simple. So here's the theorem. If you take the curved Cartan complex and add this quadratic invariant function as a curvature, the resulting category is semi-simple, or the equivalent one that's semi-simple, with one generator for each integral regular coadjoint orbit in G, which is identified with G star using the quadratic form. And you can be more precise, a generator for each orbit is the Atiyah-Bose-Shapiro-Thom class of the orbit. So what one notices, it's in a way it's a key part of the theorem, is that if you turn on this Casimir twist, the category, which a priori lives over the Lie algebra model group, or Cartan algebra model Weil group, will live there. The category is in fact supported on the regular part. And there, the complex is Morita equivalent to the one coming from the torus. So actually, somehow, turning on this quadratic twist abelianizes the group. Immediately you get back to the maximal torus in the Weil group. Now, what do I mean by the last sentence about the Atiyah-Bose-Shapiro-Thom class? Well, if you take the standard quadratic function on Cn, then it turns out it's really Knurrer periodicity in some form. The matrix factorization category is equivalent to modules over the Clifford algebra with the same defined by the same quadratic form. And specifically, there's a Koszul equivalence between the categories, similar to the one between symmetric and exterior algebras. It's a quantization of that, if you like. And it's mediated by a very specific curved complex. We write the even, the odd parts of the Clifford algebra as bundles over Cn. And you write the operator of Clifford multiplication with a vector, x, depending on your position x. So at x, just multiply by x. And notice that the composition is, of course, the square of Clifford multiplication by x, which is this quadratic form applied to x itself. The difference is that to write the Atiyah-Bose-Shapiro-Thom class, you just write this. You would want a complex. It's a two-term complex. Whereas in curved algebras, you write a curved complex, so you write the other direction as well. And it's a very strong rigidification of the Thom class for topologists. The Atiyah-Bose-Shapiro-Thom class, topological notion, well, you have a nice model for it, but you could spread it out over a bigger area and you wouldn't be any wiser. But this one is strictly supported at the origin. It's pinned there. All right, and here is the result, the proof of concept, if you like, for a trivial gauge theory. If you take the curved Cartan complex of a point, as it was here, and add to the quadratic Casimir an arbitrary invariant polynomial of greater degree, and you also do something I can't explain today, take the trace which is induced from the volume form on G, the constant volume form, then the category you get generates Witten's topological Young-Mills theory of topological twisting, quadratic Casimir class plus P as a cohomology class in BG. So you can actually compute those integrals from this model, a B-style Landau-Ginzburg model, and recover the integration formulas. So if you like, it's like a B mirror of point mod G, a B model mirror of point mod G. And I put an epsilon here because you must treat this guy as a perturbation of the Casimir, so order by order in epsilon. Otherwise, just like, I mean, that's what Witten does as well. In his case, it's because when the path integral, of course, this has higher degree than 2, so it completely wrecks any possible calculations you do. So you have to treat the couplet to a nilpotent variable. And you're still integrating against the standard Yang-Ming's functional. In our case, well, again, this will dominate completely the Casimir, so the critical points will move completely uncontrollably if you honestly turn on this polynomial. So it has to be a perturbation. All right, let me illustrate for a torus, because in that case the Cartan complex is kind of easy. So in that case, the curved Cartan complex, just a bunch of copies of a Lie algebra labeled by the weight, by the characters. The potential is this linear function, depending on the weight, plus now a quadratic function. And surprise, now every sheet has a unique Morse critical point. Psi is minus lambda. Before only the 0 sheet had critical points, and it was all a critical point. And what you want to notice is that the critical points, the way they arise, they're pulled in from infinity. In other words, if you start turning on this quadratic term by putting an epsilon factor in front, the critical point is at lambda over epsilon. So it is not something that's visible in perturbation, the order by order computation. You have to take it seriously as an honest curvature. And here's the Lagrangian interpretation. Okay, so here I've tried to draw the cotangent bundle of T checks, but I've put the torus here vertically and the fiber horizontally. It's that kind of picture. So here is the 0 section. Horizontally is the fiber over 1. And this curvy thing is the fiber over 1 moved by the Casimir flow. So this quadratic Casimir gives you a function of the cotangent bundle, purely quadratic along the fibers. So its flow becomes linear on the fibers, begins to tilt this vertical fiber. And tilting it, of course, makes it project onto the torus T check by the exponential map, so it winds around and around and around, and comes back to intercept the fiber at 1 at this regular interval corresponding exactly to the weights. So if you, I mean, both of these things are perfectly well defined smooth Lagrangians, therefore they should correspond to objects in the Kapustin-Rosansky theory. Their home would be supported at these points, and in this case they have transverse intersections, so their home will give you a copy of the category vector at each point, which is what you compute from the curved algebra, from the Cartan complex. The fixed point category will be home from this fiber to the, so this is our curved category. It's a fixed point category. So why did I draw, I've actually made a statement I hadn't explained. Why did I draw this curvy thing, the Hamiltonian movement of the fiber in response to turning on a Casimir operator? Well, because that's what it is. Now remember, what we're doing now is we're collapsing the grading mod 2, and without that the story would not exist. In fact, this story could not exist because this fiber has degree 2. So you couldn't possibly have this movement mapping into something of degree 0. It's only after collapse of the grading mod 2 that this story exists. So let's look at the deformations of a trivial representation, vect 1, of the category of coherent sheaves in the Z2 grade world. Well, general nonsense theory tells us it's controlled by a derived endomorphism of the tensor unit in the first endomorphism category. So you compute the derived endomorphism category of vect1 as a module over this tensor category. That's a tensor category. It has an identity. Its derived endomorphism ring is going to be a Gersten-Haber algebra, and it's going to control the deformations of this module. So you're in a category 5. If it was algebras over a ring, you just compute this X and stop. In the higher categorical world, there's one more step before you get to a vector space where you can say that you can control deformation theory. So the category, if you compute it, is going to be DXT hard to read. It's going to be the category of modules over the exterior algebra generated by the cotangent space at 1. Then the tensor structure on it, you have to check that out, is not going to be the tensor structure of modules over this, but it's going to be the Hopf tensor structure, so treat it kind of as a group, meaning a tensor over C. So a tensor unit is actually C, the module C, the augmentation. So when you compute the endomorphism, you have to do another X, and that leads to a symmetric algebra on T star. So that is the deformation. These are the infinitesimal deformations of the representation, the trivial representation as a representation of the group. And since it's all even, there will be no obstruction, so in fact you can expect to exponentiate them. I don't know how to write a model for the exponentiate deformations, but clearly they have to exist. And one can also show that for a general group you get the cohomology of BG. Oh, I lied. There's a part here, sim1, which is just T star. And those are obvious deformations because just move the point 1 inside the torus, T check. The tangent bundle of T check is T star. And the most movements of the point are just this obvious degree 2 part here. And here's finally the reinterpretation of the extra curved Cartan complex. So we have Cartan complex here, the differential in the curved Cartan, and the old curvature, the standard one, plus now invariant polynomial in the Lie algebra. And the claim, I can call it a theorem because I can prove it with some assumptions, is that it computes the derived, non-perturbative, twisted coinvariant category. So twisted means A, the original category A, tensor, the deformed representation. So here's an example that's somewhat useful. So let's take a point, the dual torus, tau is not equal to 1. Then you have a trivial representation, trivial module over this, the fiber functor at 1 over this, the fiber functor at 1, and the fiber functor at tau. And they live in different places, so quite naturally they're disjoint. The tensor product is 0. But after the Casimir twist, you can actually find that the tensor product becomes semi-simple, infinitely many copies of vect. And that's because you can compute it by the Cartan complex, and you get the curvature. This would have been the uncurved Cartan complex, and then you have an extra linear term coming from log tau in sim1 of T star. But that still has a more critical point on each sheet, exactly 1. You just displace it slightly. So on each sheet of the Cartan complex, you get exactly 1 copy of vector. So here are 2 points which are far away, and yet they intersect. They intersect after you add a quadratic, so P is Casimir. After you add the deformation by quadratic Casimir. And in terms of the previous picture, the story is that, well, you take this fiber over 1, you could take the fiber over another point, tau. Of course, they're disjoint. But as soon as you start flowing by the Casimir, of course, it begins to wind around and intersect again the fiber. No matter how small epsilon is, you're beginning getting infinitely many intersects. They're of course very far away from the 0 section, so they would not be visible if you just compute in the neighborhood of a 0 section. So So that's why I call it a non-perturbative effect. And this is only possible because we've collapsed the grading mode too, because otherwise these directions would be graded and therefore conical. So no such curving would be allowed. Well, because you cannot compute it order by order in the category of modules over this. If you compute it order by, you get 0. And that's because it's not in the neighborhood of a 0 section. That module category only sees the neighborhood of a 0 section. In that sense, non-perturbative. And it's also, if you like, the expansion is a graded variable, and it only can become convergent if you decide to ignore the grading. You suddenly declare that degree 2 actually is 0, so it makes sense to talk about entire analytic function, that variable. Alright, so now let me stop pause for a second, because what I'll try to do now is to put everything together with that curved Cartan space, and then give a lower dimensional analog, and finally a comment on further directions. Actually, it's 4:30. So, on one hand, we could take a break. On the other hand, this is the conclusion. So, probably in 10 minutes, I can cover the 3 sheets, and then we can everybody can leave, and then I can discuss with myself the fine points of the theory. What do we vote for? 10 more minutes? Okay, good. Thanks. Okay, so let's recall the space. The space was the affine blow-up of some affine blow-up of the cotangent bundle of the torus divided by the Weyl group, blowing up the root hyperplanes and their counterparts in the torus at the same time. But more uniformly, we describe it as the regular part of the cotangent bundle of G, holomorphically reduced by G check, and even more uniformly, that's of course the theorem of these chaps, the spectrum of the equivariant homology of the base loop. So I drew the picture for G is SL2 and G check is PSL2 again. Looks like I changed again. So here's the projection to the group, to conjugacy lies in the group, T mod W. Vertical, the projection to the Lie algebra mod W. Pink, the exceptional fiber, there's only one here. In general, there's one most exceptional fiber, actually one copy of it over each element in the center of G check. If G check was SL2, there'd be another copy maybe here. And that spec of the homology of omega G, also a polynomial ring. This in blue is the vertical, or the proper transform of the vertical fiber over 1, and intersections with this compute the fixed point category. In light blue, there's the support of some G category of the G action, realized as an object in this Kapustin-Rosansky-Witten 2 category, and this is its support. So the blue circles give the intercepts with the vertical line, and this is where the fixed point category lives. If they're transverse, just get a copy of vect at each point. If not, you get something like matrix factorizations. But actually, I'm lying because it depends what C was. It's conceivable that C was a whole space mapping to it, and then you just get the fibers at those points. So that was a bit hasty. The pink points are the intercepts with the 0 section, and that's where the original category lives. That is, remember, home from the regular representation to C, and that's C. So the category C is only supported in the formal neighborhood of the pink sector. Right? The underlying category. So this object in the KRW is much bigger. So you can ask what it means. And for that, let's stay in the analytic world, not C infinity or something. This is a holomorphic story. So if you have the analytic germ of an object here, I mean, it's reasonable to assume that if we do have this convergent deformation theory, that we can continue it analytically or not. We continue until we cannot continue anymore. So from that point of view, what's outside, what's away from the category, the new information, is not so much new information. It's already contained there. It's just that you're hitting constraints when trying to extend. At some point you hit singularities, essential singularities. So I think the better question to ask, starting with a category which will only be depicted here near the pink points, let's analytically continue to an object in the KRW category. What's the meaning of that, or the meaning of the points we have not seen yet? Well, the answer is yes, you can find the meaning of that, but not by taking fixed point categories, but by taking twisted fixed point categories. Because you can sweep out the BFM space by Hamiltonian displacements of this vertical fiber. In fact, the generating Casimirs will give you constant flows in the pink fiber, so in the neighborhood of the pink fiber, in fact, you even foliate the space. And here is in black, is a Hamiltonian displacement of F, and its intercept here detects the topologically twisted gauge theory, gauge category. So in other words, having the object defined everywhere in this BFM space defines for you the gauge theory and all its possible topological twists. And if this object, on the contrary, encounters some nasty singularity somewhere, that will tell you that if you start computing the topological twists and try to, say, analytically continue the partition functions, you're going to hit singularities when this moved fiber hits nasty parts of the object. So this contains the information again about the original object, its group action, and all the topologically twisted gauged versions. Should mention in the torus case, if you want to just sweep out, explore the space, there's just the cotangent bundle, and then linear Hamiltonian suffice, and you just foliate the cotangent bundle by the vertical fibers, and that gives you the spectral decomposition of the category. And here I'm saying if a support is not closed or has singularities, then when you try to analytically continue some topologically twisted gaugings, you run into trouble.
And this is not, no matter what G category you took, it always sort of sees the whole?
Well, if you start with just with the category and the G action, what you start with is technically the formal neighborhood of the pink section. And then you have to analytically continue. But I think with reasonable definition, which you don't quite have of this KRW space, the analytic continuation, if it exists, is unique, just like our functions. Therefore, the rest of the stuff is actually determined. By performing it, what you're learning is you learn where you're going to have trouble gauging the category, what topological twists are going to be bad. That's sort of what's happening. I mean, I wouldn't know what to tell you if somehow you set up as a model in which you don't have unique analytic continuation. In that case, there's just some extra information here which has not been specified by writing down the category and the group action on it. That's all it would mean. But I mean, one expects that for reasonable objects, you should have unique analytic continuation. Okay. I could have started my lectures with this, but you would have thought I was crazy, which maybe you do anyway. But there exists a lower dimensional analog for this, and involves group actions on vector spaces or complexes of local systems over BG and equivariant cohomology. The lower dimensional analog is equivariant cohomology for a chain complex with trivialized G action. And what you do is you take the equivariant cohomology with coefficients in V and view it as a module over the cohomology of BG with constant coefficients, which is just a function, invariant functions on the Lie algebra. So this guy is a sheaf fibering naturally over T mod W. The derived fiber over 0, derived fiber of this sheaf that you get, which is the derived tensor product, if you do it at cochain level the way you should, is quasi-isomorphic to the original complex V. So that's the analog of saying that the intercept of this blue thing with the pink section is the original category. the space of sections over the entire space is, of course, the equivariant cohomology. The space of section will be the intercept of this fiber, the blue fiber. So to make the analogy precise, you have to put on your Kapustin goggles and double the base from the equivariant cohomology of BG to the cohomology of BG to the equivariant homology of the group G. That's also known as string topology of BG, or it would be HH upper star of H star of BG. Turns out to be exactly right without, so pick up some odd generators. And it gives you an odd version of BFM space, and that's also, it's more difficult to see, a slight blow up of the torus version, the part invariant in the Weil group. It's a copy of T, an odd copy of the Lie algebra of a torus, modeled by the Weil group, and blow up a little bit. Again, you adjoin some ratios of function. This makes no sense whatsoever. Alpha odd over alpha even. Right. The odd generators are allowed to have a bit of poles if you do the calculations. So now the difference is that everything actually is set theoretically supported on F, the analog of the zero of the trivial fiber of the cotangent bundle, simply because the only thing you're adding are some nilpotent generators. Whether or not you collapse the grading mod 2, the extra stuff is always nilpotent. So everything happens always in the formal neighborhood of F. There is no funny stuff happening elsewhere. The exceptional fiber is this odd space sitting here, but it's also entirely nilpotent, so it looks like a point. And that's a situation where these Kapustin goggles reveal no new information. Everything you could compute, you can compute inside modules over this ring.
What was that?
F, it was a fiber before, it was a fiber of the cotangent bundle over 1. So it's this big thing. F remains big, the pink thing is completely nilpotent now. So you can probably guess the pattern. The pink thing was spec of the homology of omega G. Here the pink thing is spec of the homology of G. The blue thing is the cohomology of BG. So yes, you can rewrite all of equivariant cohomology in a way which literally imitates the story I told you for gauge theories, but it's a useless exercise because all the information was already there. But as a fun exercise, I'll challenge you to find some complex for which the equivariant cohomology is supported only somewhere here, not near 0. So find the 0 complex with non-trivial equivariant cohomology. And of course the hint is it has to be in the Z2 graded world. You cannot do it in the Z graded world because it would have to be conical in this direction for the same reason. Okay, and some concluding nonsense. What could you do with this going further? Well, first is a loop group analog of the story and the loop group analog of the BFM theorem describing the equivariant K-homology of omega G in terms of a blow-up, almost, of a blow-up of a copy of the torus and the dual torus. If you try to guess where it comes from, it should be a dimensional reduction along the circle of a 3D A-style gauge theory. It should be a picture for that. What I know it's connected to, at least in simple cases, is K-theoretic Gromov-Witten theory. And for the gauged point, you compute the Verlinde version of Witten's integration formulas. You compute K-theory integration formulas on the modular. You can try to guess that the collection of these theories should represent circle-reduced 4-dimensional pure gauge theory for G. And because of work of Kapustin and Witten, we think that Langland's duality should be very obvious, very salient there. So that means that the loop version of it should exhibit Langland's duality even more than what I've told you so far. And I'm happy to believe it, but I can't tell you that I've seen something that you wouldn't be able to guess from this story and from knowing loop groups, so not yet at least. If you invite me again next year, maybe I'll tell you. And finally, you can come up again with a cheap guess because there's a pattern, dimension 1 and 2. If you want to look at k-dimensional gauge theories of this form, they should be described in some way by points in objects and categorifications of this sphere topology of BG, equivariant homology of various loop space of BG. Of course, this is equivariant homology of G if K is 1, and equivariant homology of omega G if K is 2. So this gives at least a starting point of what to look for. I mean, we want to fiber the story over these spaces, but they have to be categorified sufficiently highly. I think that's what I would suggest. And now I'm really done.
All right, let's thank Constantine again for a great lecture series.